In a world full of chaos and disorder, they help maintain order. For over 100 years, they have been helping humanity, silently serving humans as they go about their day. They go unnoticed, except by the most keen observer, helping maintain the status quo that we enjoy without seeking praise. They are Transformers. But not the Transformers we know and love. Rather, these Transformers we barely recognize and acknowledge.
Sorry about that. When we think of Transformers, most people immediately think of the 1980s toys produced by Japanese toy company Takara Tomy and United States company Hasbro that has led to several TV shows and some movies starring Shia LaBeouf. They are robots who transformed or converted into various vehicles, fighting each other to the death for our own enjoyment. However, the real Transformers that have had such an impact on our lives have been around since 1880, helping transform the way we move energy from one place to another. But what exactly does a Transformer do? How does it work? And why is it important in our own lives? To answer these questions, it is important to first understand that a Transformer's function is to transform one voltage to another. A common example is most plug-in components of laptops, cell phones, and video game devices all have a transformer inside of them that converts the roughly 120 volts of alternating current into a lower voltage that is more compatible with the device being used. Transforming one voltage to another has many other important uses, but we first need to discuss exactly how a transformer transforms one voltage to another. A transformer's ability to change from one voltage to another is all dependent on important phenomenon seen in electricity. The first phenomenon is as a current goes through a wire, it produces a magnetic field because all magnetism is caused by the movement of charge, aka current. It is also important to understand that magnetic field strength is proportional to the current it is produced by. So as current increases, so does the magnetic field that it produces. Second electrical phenomenon is known as Faraday's law of induction. Michael Faraday was a scientist who ran several experiments which showed that magnetic fields could also cause currents, but only if the magnetic field changed. His experiments eventually showed that the change in magnetic field was causing a change in the electromotive force, or potential difference. Further experiments found that the crucial quantity being changed in relation to magnetic fields was the magnetic flux. Magnetic flux is the magnetic field strength perpendicular over a certain area, and is found by taking the magnetic field strength B times the area A times cosine of theta, which is the angle at which the magnetic field hits the affected area. By changing any of these three components, you will induce a change in the magnetic flux. In short, Faraday's law of induction states that the electromagnetic induction, where a magnet produces a current, is based on the fact that any change in magnetic flux induces an electromotive force. Faraday also found that the induced EMF was based on the number of turns in the coil and the amount of time over which the change in EMF occurred. Taking Faraday's experiments even further was another scientist named Emil Lenz. He found that the EMF creates a current known as I, a magnetic field known as B, that opposes the change in flux. Now that we better understand the relationship between current and magnetic fields, we can put together our understanding of these phenomena in order to explain transformers. A transformer consists of two coils called the primary and secondary coils. These two coils wrap around a ferromagnetic core that not only traps the magnetic field created by the primary coil, but the core's magnetization increases the magnetic field strength created by the primary coil. The input voltage is usually identified as the primary coil, while the secondary coil produces the transformed voltage. The input voltage is an alternating current, meaning the current is periodically reversing direction. This means that the current passing through the primary coil is changing, which then causes the magnetic field it produces to change. As the magnetic field strength changes in the primary coil, a magnetic flux being sent to the secondary coil is also changing. This change in magnetic flux induces an AC output voltage on the secondary coil. It is important to note that transformers only work if the incoming current is alternating, also known as AC. Otherwise, there will be no change in magnetic flux, and no EMF will be induced on the secondary coil. This means that direct current cannot be transformed to another voltage by a transformer. It is theoretically possible to use a switch to connect the direct current to the primary coil, but is not practical and therefore unreasonable. To understand the relationship between the input and output voltage, it is important to understand how the output voltage, or Vs, is dependent on the input voltage, or Vp, as well as the ratio of loops in both the primary and secondary coils. Faraday's law of induction states that the output voltage is equal to the EMF S of the secondary coil, assuming coil resistance is small. This means that output voltage will be equal to -1 times the number of turns times the change in magnetic flux over time, as seen in the top left corner. Lenz's law also tells us that the primary coil will oppose the change in flux, so the input voltage, Vp, is equal to the -1 number of turns in the primary coil times the change in magnetic flux over time, as seen in the equation in the top right corner. Since the area of the coils and magnetic field are the same on both sides, change in magnetic flux over time is the same for both equations. Using this knowledge, we can set these two equations equal to each other and find that the resulting equation gives us what is known as the transformer equation, which is the voltage of the secondary coil over the voltage of the primary coil is equal to the number of coils in the secondary coil over the number of coils in the primary coil. The transformer equation states that the ratio of secondary to primary voltages is equal to the ratio of the number of loops in their coils. Depending on the number of loops in both coils, the output voltage can be lesser than, greater than, or even equal to the input voltage. A step-up transformer is one that increases voltage, while a step-down transformer decreases the voltage. If you ignore resistance in the transformer, the electrical power going into a transformer will be equal to the electrical power coming out of it. Using the power equations for input and output, we can rearrange the equations and find that the ratio of the output voltage over the input voltage is equal to the ratio of the input current over the output current. Or in simpler terms, as voltage increases from the primary to the secondary coil, then the current will therefore decrease, while a decrease over voltage will result in an increase in current over the transformer. So now we know what transformers do and how they do it, but why is that even important to us? One of the most important uses of a transformer is being able to transform the voltage of the incoming electricity into our homes. Most power plants produce electric power that is greater than 10,000 volts. When we're talking about electricity, the higher the current, the more movement of charge there is, meaning there will be more collisions inside the wire, causing more energy to be lost in the form of heat. Since we don't have the convenience of having power plants every block, to limit the loss of energy as electricity travels far distances, step-up transformers will transform the roughly 12,000 volts produced by the power plants to an even higher voltage of around 400,000. Then, as the electricity gets closer to your home, substations that act as step-down transformers will transform the energy back to around 13,000 volts. Then finally, the electric poles by your home have another step-down transformer that converts the power to about 240 volts. Imagine if we didn't have transformers. If you tried connecting your toaster, it would explode. Transformers allow for the various electrical needs of different places, such as a factory needing to power large machinery and you needing to power your smartphone to continue your binge watching of The Office, to be met. Without transformers, our ability to move electricity and power, everything we use in our day, would be severely impacted. So the next time you're charging your laptop or watching TV, make sure to keep in mind how transformers are always there, saving the day.
Transformers, saviors in disguise.